We're going to start our unit on quadratic equations. The different methods of solving a quadratic equation is by graphing, which we'll take a look at in section 4.1, by factoring, which we will look at in 4.2, completing the square, which we will look at in 4.3, and the quadratic formula, which we will look at in 4.4. So for this section, we're going to be taking a look at graphing we're going to look at graphical solutions of quadratic equations. So you can solve a quadratic equation of the form ax squared plus bx plus c equals 0 by graphing the corresponding quadratic function f of x equals ax squared plus bx plus c. The solutions to a quadratic equation are called the roots of the equation. You can find the roots of a quadratic equation by determining the x-intercepts of the graph or the zeros of the corresponding quadratic function. So just to take a look at the difference between equation and function. So I have an example here, 3x squared plus 2x minus 1 equals 0. This is our equation. This is what you're going to be asked to solve. They'll say, solve the following equation. And as you can see from this one here, you'd be solving for x. If you are asked to solve the equation by graphing, then you need to write its corresponding function. So in this case, f of x equals 3x squared plus 2x minus 1. Or if you like, you can write y equals 3x squared plus 2x minus 1. And this is your function. So the solution to the quadratic equation is called the root or the roots, depending on how many you have. You can find these roots by finding the x-intercepts of the graph of the function. And another way to say finding the x-intercepts would be to find the zeros of the corresponding quadratic function. Okay, now if you have a TI graphing calculator, then you're going to be looking for zeros. And if you have the Casio calculator, you're going to be looking for the roots, and they really mean the same thing. So just a few notes of explanation. Okay, so quadratic equation. First of all, it's a second degree equation with standard form ax squared plus bx plus c equals 0, where a can't be equal to 0. Now we talked about this in an earlier lesson. A can't be 0 because if I plug a 0 in here, then my x squared term disappears and I'm left with a first degree equation function, which you know is a linear function, and when you graph that you get a straight line. So this one is second degree, you can tell because the highest exponent is a 2. An example of a quadratic equation would be like 2x squared plus 12x plus 16 equals 0. So roots of an equation. When we talk about the roots of an equation, we are talking about the solutions to an equation. You can have one, two, or no solutions. Okay, so when you have a quadratic equation, there's possibility of one solution, two solutions, or no solutions. The zeros of a function, these are the values of x for which f of x equals 0, or if you like, y equals 0. And remember, when you set y equal to 0, that means that you want to find your x-intercepts. So the zeros of your function are related to the x-intercepts of the graph of a function f of x. Okay, so that ends our introduction. In our first example, we're going to solve a quadratic equation that has two distinct real roots. What that means is that you have two x-intercepts. You're going to be using your graphing calculator, so if you want to go get that. You are asked to solve the quadratic equation negative 2x squared plus 12x minus 11 equals 0 by sketching the graph of its corresponding function using your graphing calculator. In your graph, include the vertex, x-intercepts, y-intercept, and the axis of symmetry, and label your graph clearly. So here's our equation, and by looking at it, if they would ask you to solve, you know you're looking for x because that's the only variable you have. But if we're going to solve by graphing, we need to write its corresponding function. Which is f of x is equal to negative 2x squared plus 12x minus 11, or if you like, you can write y equals negative 2x squared plus 12x minus 11. I'm going to use the Casio calculator to graph this, and I have already entered in the equation and set my window settings so that they would match the ones that are here. So my x min is negative 2, my x max is 8, my y min I put at negative 15, you can go negative 14, and I put my y max in as 8. Okay, so I'm going to graph, and you should get something like this on your calculator. Now you've been asked to find several things. You've been asked to find the vertex, the x-intercepts, the y-intercept, okay, and then graph the axis of symmetry. So let's start by looking for our vertex. Now you can tell by looking at our parabola that this is a maximum, and you know that you can determine that from your equation because a is negative. That means that your parabola will open down, and if it opens down, it's going to have a maximum. So we're going to look for our max. So I'm going to go for F2, and we can see that our maximum is when our maximum is 7 when x is equal to 3. Okay, so we have a vertex at 3 and 7. We also want our x-intercepts, so I'm going to go back to my G-solve. And in the Casio calculator, that would be your root. If you're using the TI-83 or 84, you're looking for your zeros. So we want our roots, so we press F1, and here's our first root. We're only going to work to the nearest tenth, so our first root is when x is equal to 1.1. And to get our second one, we will hit our right arrow key, and we also have a root at 4.9. Okay, so our x-intercepts are at 1.1 and 4.9. We also want our y-intercept, so we go back to our G-solve, and we want y-intercept here, so F4, and we can see that our y-intercept is at 0 and negative 11, so our y-intercept is negative 11. So we're going to graph those points, we're going to sketch them, and then fill in the blanks below. Alright, so we have a vertex at 3 and 7. We have one x-intercept at 1.1. And our second x-intercept is at 4.9. We have a y-intercept at negative 11. And we will have a axis of symmetry that goes through where x is equal to 3. So we draw a dotted line through there and label it x equals negative 3. And so we will draw our parabola in. Alright, and this is what we get. So the graph crosses the x-axis at the points 1.1 and 0 and 4.9 and 0. The x-intercepts of the graph, or the zeros of the function, are 1.1 and 4.9. Therefore, the roots of the equation are 1.1 and 4.9. And these are the solutions. So you can see that the roots of your quadratic equation are these solutions to your quadratic equation. And this ends example 1. In our second example, we're going to take a look at solving a quadratic equation that has no real roots. So what do you think that no real roots means? If you guess that it means no x-intercepts, you're right. So that means that when you graph this, the graph will not cross over the x-axis. We're going to solve 2x squared plus x equals -2 by graphing. We're going to rewrite the equation in the form of ax squared plus bx plus c equals 0. Okay, so that means we're going to move the -2 to the left. When we do, it becomes positive. So we'll leave the 2x squared where it is, the x where it is, bring the -2 over, it becomes +2. And because we've removed the -2 from the right-hand side of the equation, what we're left with is 0. And that's why we would say equals 0. So why do you rewrite the equation in the form of ax squared plus bx plus c equals 0? Well, partly because of the reason I just gave you. If I remove that -2 from the right and bring it over to the left, we have 0 on this side. But the real reason is because we want to find the roots. So when we set y equal to 0 in the corresponding function, right? So the corresponding function for this, I'll just write that down, corresponding function is y equals 2x squared plus x plus 2. Okay, so when we set y equal to 0, we mean that we want to find the x-intercepts. Okay, and because we want to find the x-intercepts, we are looking for the solutions. So, and therefore, so these 3 dots means therefore, the solution or solutions. So we're going to use the same instructions as above to graph and solve. So we're going to use the corresponding function. Y equals 2x squared plus x plus 2. We're going to enter that into our graphing calculators and find our vertex, x-intercepts, y-intercepts, and so on. You can use your table function on your graphing calculator to get extra points, and I will explain why in a moment. So let's start by graphing. When I set up my window settings in my graphing calculator, I use the ones that are on the graph here. So my x-min at -6, my x-max at 8, my y-min at -4, and my y-max at 8. And I got this graph. Okay, so we want to find the vertex to start with. So F5, and you can see that our graph gives us a minimum. So I want minimum, And I can see that my vertex is when x is negative 0.25 and y is equal to 1.875. Okay, and I'll just round that to 1.9. We can get a y-intercept, so let's go back to our g-solve, y-intercept at f4, and we have a y-intercept at 0 and 2. But if we go back to our graph, okay, you can see that because the vertex is above the x-axis and our parabola opens up, it doesn't cross the x-axis, so we don't have any roots, right? No x-intercept, so we don't have any roots, okay? And that's why when you have no real roots, you do not have any x-intercepts, okay? Now, if we want to graph some extra points, there's a couple of ways you can do this. Now, in your notes, it says to use your table function. One other way that you can do this, you can go to your g-solve and press F6, and we're going to look for values of y when I just plug in some x values. So F1. So let's find out what y is when x is 1. So I'm just going to press in x is 1, execute, and I can see that when x is 1, y is 5. So that'll give me a point on the right of my vertex. I want to get a point to the left, so I'll go back to F5. Oops. Wait a minute. Okay, so draw. All right, so F5, and this time I want to pick something to the left of my vertex. Okay, and I could go with -1, but I'm going to plug in -2. Oops, sorry, I should first press Y-calc. Okay, so -2, and execute, and when x is -2, y is 8. Okay. Now, the other way that you can get some extra points on your graph is to use your table function. So if you have the Casio, you want to go back to your menu, and you want to go to Table, and you want to set your table. And where I've set it is, I'm going to start when x is -3, and I'll end when x is 5. And the scale that I'm going to use, or the step if you like, is I'm going to go up by 1s. And so I'm going to execute that, and then execute again, and here's my table. So these are some points on the graph, -3 and 17. But as you can see, that would be off of the graph here, so I don't really want that point. Here's the -2 and 8 that I found earlier. If you want, when x is -1, you can plug in, or you can graph -1 and 3. 0, 2, there's your y-intercept. And here's the 1 and the 5 that I found earlier. And we could plug in x's too, but if you notice, our y value is 12, and that would be off of our graph. Okay, so 2 ways that you can find extra points on your graph. So let's start by graphing our vertex. Our vertex is at -0.25 and 1.9. So -0.25 around here and 1.9 about here. Okay, so -0.25 and 1.9 is our vertex. I found 1 point when x is 1 and y is 5, so here is 1 and 5. And my second one I found was -2 and 8, which is here, so we can just join those points and graph our parabola. All right, and one other point, almost forgot, our y-intercept at 0 and 2. Let's draw in our axis of symmetry, which goes through where x is equal to -0.25. So draw a dotted line through that and label x equals -0.25. So, how can you tell from the graph that this quadratic has no real roots? Well, you can tell by noticing that you have no x-intercepts on your graph. So there are no x-intercepts. Therefore, no real roots. And therefore no solution. And another way to write that is just a 0 with a line through it. No solution. Okay, so that's example 2. In our next example, we're going to take a look at a quadratic equation that has one real root. And just think about a moment what one real root means. Okay, so if 2 real roots means 2 x-intercepts and no real roots means 0 x-intercepts, then what do you think one real root means? So if you guess that it means 1 x-intercept, you are right. We're going to do this question without our graphing calculators. We're going to use the paper and pencil method. You are asked to find the roots of the equation x squared minus 6x plus 9 equals 0 and then verify your answer. So we are going to graph it. We're going to use a table of values to graph it. So it's really important that you find the vertex by using the vertex formula. What I want to do first, though, is just to show you, using our first example of negative 2x squared plus 12x minus 11 equals 0, as an illustration as to what your table should look like. So I did it on the TI-83 calculator because the table is much easier to see on this calculator, and so it's easier to see some patterns. So I've already entered the equation in and set up my table, and here you have it. So all of your x coordinates on the left and all of your y coordinates on the right. I have the vertex highlighted. So the vertex on our first question was at 3 and 7. And you can see by looking at the y coordinates the symmetry of your parabola, and that's what you're going to be looking at when you set up your table of values. So the first thing that you want to do is to come up with your vertex, and we're going to use our vertex formula for that. We want to put it in the middle of our table, and then we want to pick some values for x that are smaller than the x value of our vertex. So on here, our x value for our vertex is at 3, so the number smaller, I'm going to pick 2, 1, and 0. And you want to pick some numbers that are bigger than that 3, so 4, 5, and 6. All right, and then you should see that there's symmetry on your graph. Negative 11, negative 1, 5, 7, here's your vertex, and then the numbers 5, negative 1, negative 11 repeat themselves. So that's what you're going to look for when you set up your table of values for this question. So for our vertex, we need to write out our values for a and b, right? Because we've got those two constants that we want to use for our formula. So according to our quadratic equation that we're asked to determine the roots of, we can see that a is equal to 1 and b is equal to negative 6. So you want to pick the negative in front of that 6. So let's find the x coordinate to our vertex, negative, and then we want to plug in b, which is negative 6, all over 2 times a, which is 1. That will give you 6 over 2, which is 3. So far for our vertex, we have an x coordinate of 3. Now we want to find out what the y coordinate is for our vertex. We go back to our equation. We want the corresponding function, so I'm going to write y equals x squared minus 6x plus 9, and the reason why I want my corresponding function is because I'm looking for the y coordinate of my vertex, and so I need to write my equation in vertex form so that I can actually solve for y. So I want to find out what y is when x is 3, so I'm going to plug in 3 for my x's. And I'm going to simplify all that, so 9 minus 18 plus 9, and I get that y is equal to 0. So I can see that my vertex is at 3 and 0. So that's the first point on my graph. Now, what I want to do next is to generate a table of values and plot the points. I want to place the coordinates of the vertex in the center of the table, and I want to choose values for x that are smaller than my 3, and I want to choose values for x that are larger than my 3, and find the corresponding y values. Alright, so in the middle of my table, I'm going to put my vertex. There's your vertex. I want to choose numbers which are smaller than 3, so 2, 1, and 0, and I want to pick numbers that are bigger than 3, so 4, 5, and 6. I'm going to go back to using my function, and I'm going to write it as f of x this time. And I'm going to go to my table, and I'm going to find what f of 2 is. So plug in 2 for x, and you find that you get 1, and so you have a point at 2 and 1. Next, I want to find out what my y coordinate is if x is 1. So I'm going to find f of 1, and I'm going to plug in 1 for x this time. And I get 4. And so I have a point on my graph which is 1 and 4. And then I'm going to plug in 0 for x, so I'm going to find f of 0. And I get 9. So I have a point at 0 and 9. Now, because my graph is going to have symmetry, I can rewrite the numbers 1, 4, and 9 below the 0, starting with the 1, so 1, 4, and 9. And now I have 7 points that I can use to graph my function. Okay, so my first point is 2 and 1. And then I have 1 and 4. And then I have 0 and 9. Okay, and I'm going to include the coordinates for this one because this is your y-intercept. And then I have a point at 4 and 1. I have one at 5 and 4, and 6 and 9. And so here is my parabola, and my axis of symmetry is right here at x equals 3. Now, if you take a look at this graph, you can see that you have only one x-intercept. It happens to be the vertex. So if we go down, we can fill in the blanks. So the x-intercept of the graph occurs at the point 3 and 0 and has a value of 3. The 0 of the function is 3. Therefore, the root of the equation is 3. Okay, so this means that you have one solution. Okay, so remember at the beginning of this lesson I said that you could have two solutions, one solution, or no solution. So you get one solution when your vertex is on the x-axis. You also want to verify your answer. So we got an answer of 3 and 0. So we're going to take our function, f of x is equal to x squared minus 6x plus 9. We're going to plug in 0 for y, and if you recall, f of x is our y coordinate, so we're going to plug in 0 there. And we're going to plug in 3 for x, And so we get that 0 is equal to 9 minus 18 plus 9, which leaves you with 0 is equal to 0. So remember, when you're verifying, you want the left side of your equation to equal the right side. So we've shown that. We've shown that the left side is 0 and the right side is 0. So we have verified that our solution 3, 0 is indeed the right answer. And another way that we want to look at this too is we want to show that 3, 0 is an x-intercept. And we would want to do that by showing that y is equal to 0. Okay, if we can show that y is equal to 0 when x is 3, then we also know that we have an x-intercept. Okay, and that concludes our discussion. Our last example, example 4. Solve a problem involving quadratic equations. The Mackinac Bridge is one of the longest suspension bridges in the world. This bridge spans the 8-kilometer wide Straits of Mackinac, where Lake Huron and Lake Michigan meet. Find the length of the main span to the nearest 10 meters by solving the corresponding equation of the function h of x equals 0.00031 x squared minus 0.36x, where x is the horizontal distance between the towers in meters and h is the vertical distance from the top of the towers and the cable in meters. Sketch a graph of the quadratic function and label the vertex, x-intercepts, and y-intercepts. Okay, so you're being asked to calculate the length of the main span on this bridge. What you're looking for is the distance between one tower and the next. Okay, so this is the main span. Okay, when we're talking about horizontal distance between the towers, we're talking about the horizontal distance between the towers at any point between them. Okay? But that's with respect to the cable. So I'll just draw the cable in here. It looks something like this. Okay? So when we talk about horizontal distance, we're talking about the distance between the cable and between the towers at any point. The vertical distance then is from the top of the towers, so this red line, down to the cable. Okay, so that's h. That's your vertical distance. That's your up and down distance. And that can be, once again, anywhere between the top of the towers to the cable, so all the way along the whole length of the main span. Now, we're going to use our graphing calculators to determine the main span of the bridge, okay? And just understand, though, that when you want to determine any value for x in this function, you need to use its corresponding equation. And in this case, 0.00031 x squared minus 0.36 x equals 0. Okay, so this is the equation that we're solving, and we're going to use our graphing calculator to do that, so we need to use this function. Now, I've already put all my information into my graphing calculator, so I'm just going to give you the window settings. Okay, so for the x min, I put in -10, and I figured because this bridge is 8 kilometers in length, then these towers have to be, you know, quite a substantial distance apart from each other. So I made an estimate of approximately 1,500 meters, which is 1.5 kilometers. So I used a scale on my x-axis of 100, and I went up to 1500 meters. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So there's your 1500 meters. And along the y-axis, I started at a max of 10, and I went down to minus 120. So I used a y-scale of 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's negative 100, and 2 more, we're at negative 120. So what I'd like you to imagine is that the cable between the two towers is going to be situated below the x-axis, and the tops of our two towers are going to be points on the x-axis. So we're going to have like one main tower maybe here, another main tower here, and the cable will run in between them. Okay, so let's take a look at what we get on our graphing calculator. So if you put these window settings into your graphing calculator, you should get this graph. And if we're going to situate our x-axis along the top of the towers, then where the cables meet this red horizontal line on the diagram is going to be, or are going to be, our x-intercepts. So we're looking for roots, or if you have a TI calculator, your zeros. And so we go for roots, and you notice that our first root is at 0 and 0. Okay, so that would be at the origin. That means that the top of this main tower here, or this one of these towers here anyway, is at 0, 0. And also note that your x-intercept at this point is also your y-intercept. Remember, y-intercepts occur when x is 0. So here we have x equals 0, so we have a y-intercept at 0. Okay, so our other root is at 1,161 and 0. So we're going to plot those 2 points, 0, 0 and 1,161 and 0 on our x-axis, because that's where our roots are. And if you imagine that the parabola that we have on your graphing calculator and on this graphing calculator is the cable, and I asked you to graph the vertex, then the vertex would have to be at the lowest point on our cable. Okay, so we have a parabola that's opening up. We're looking for a minimum point, and our minimum point is at 581 and negative 105. So we're going to graph those 3 points, our two x-intercepts and our vertex. Okay, so 1 point at 0, 0. Okay, and so remember, that's your x and your y-intercept. Now, when I ask you to label your intercepts, your x-intercepts and your y-intercept on the graph, I don't mean for you to draw an arrow at the point and write x-intercept. What I want you to do is to write the ordered pair. Okay, and your other point was at 1,161. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Here's 1,000. Here's 1,100. And 61 is approximately here. So we have a point at 1, 1, 6, 1, and 0. Our vertex is at 581 for x. So 1, 2, 3, 4, 5, 81 around here. And our y-coordinate for our vertex is down at negative 105. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Here's 100. Minus 105 is here. So we can plot our vertex approximately here at 581 and negative 105. Okay, so we're going to draw our parabola in, and our parabola is a model of our cable. And like I said earlier, if you can imagine that your cable is joining the tower at this point, then your y-axis here is going to be one of your towers, and your cable over here is going to attach to the second tower, so you can imagine that your second tower is here. So maybe I'll just draw that in. Okay, so here's one tower, and here is the second tower. So that's a tower, and that's a tower. So what we want to know is, what is the distance of the main span? So that means from the top of one tower to the top of the other tower. So that means along the x-axis here. So we want to know that distance. So we need to take the difference between our first x-intercept and our second x-intercept, which is 0, and we get 1,161. So the distance between your two towers and the distance of your main span is 1,161 meters. Okay, so one other thing, because we're asked to find the distance to the nearest 10 meters, okay, then what we want to do is take the 1,161 and round it to the nearest 10. So the 1 here is in the 1's column, and the 6 is in the 10's column. So what we want to do is we want to use the 1 in the 1's column to round the 6. Now because the 1 is less than 5, we're going to leave the 6 as it is. So to the nearest 10, our distance is 1,160 meters. Now let's say that we had a 5 in the 1's column. Then we would use that 5 to round the 6 up to 7, and then to the nearest 10 would have been 1,170 meters. Okay, so we're ready to write our final sentence. The length of the main span to the nearest 10 meters is 1,160 meters. So that concludes section 4.1.